Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 2nd, 2026, about 4 days ago. It introduces a fully dynamic reinforcement learning framework that boosts agent performance by over 9% on the OS World Computer Control Benchmark. The paper is titled RLAnything, Forge Environment, Policy, and Reward Model in Completely Dynamic RL System. And as we'll see shortly, the fact that its optimized reward model can outperform human supervision is a really significant finding. And for those interested in the implementation, the authors have shared their code on GitHub. Figure 1 summarizes the key experimental results across 3 distinct domains. On the left, for the OS World Computer Control task, the RLAnything model, shown in blue, outperforms the Claude 3.7 Sonnet baseline, reaching over 40% accuracy. In the middle, on the live bench coding benchmark, we see a similar jump, rising from about 36 to 43%. Finally, on the right, the performance on the AlphaWorld text game is particularly striking, where the model improves upon QN 2.5 by nearly 20 percentage points. Figure 2 lays out the 3 pillars driving this performance. On the left, Panel 1 shows the policy training, which integrates both final outcomes and detailed stepwise rewards, ensuring the agent gets dense feedback throughout long trajectories. Moving to the center, the reward model isn't static. It is jointly optimized via consistency feedback so that its step-level judgments align with the final results. Then, on the right, the environment itself adapts scaling task difficulty based on critic feedback to keep the challenge level optimal for learning. While the previous diagram outlined the theory, Figure 3 demonstrates this environment adaptation in practice across 3 domains. The top panel illustrates a computer use task where the agent initially fails to calculate an employee's age, scoring 0 accuracy. Here, the reward model identifies that the agent is misreading the interface, so the system simplifies the task by injecting specific hints to guide the policy. Conversely, the bottom panels show the opposite adaptation. For both the text game on the left and the coding task on the right, the agent succeeds too easily, so the critic increases the difficulty by introducing rarer objects or stricter logic constraints to keep the learning curve steep. Alright, Table 1 now breaks down the specific contribution of each dynamic component across the 3 domains. The rows track the performance as we add pieces, first optimizing just the policy, then adding the reward model, and finally including the environment adaptation. Looking at the GUI agent section, the full RLAnything framework achieves the highest accuracy, boosting out-of-distribution performance to over 21%. We see even larger gains for the LLM agent on the right, where the final row jumps to over 60% in domain. The bottom half confirms this trend for coding tasks like Live Bench, where the complete system consistently outperforms the simpler baselines. So, Figure 4 visualizes these gains as training curves over time, confirming that each added component lifts the model's potential. On the left, for the AlphaWorld text game, the yellow baseline plateaus early, but the red line, representing the full RLAnything system, keeps climbing steadily to 60% accuracy. We see the same pattern on the right for OS World. Here, the red curve separates clearly from the blue and yellow lines, showing that dynamically adapting the environment and rewards allows the policy to learn much faster and reach a higher peak. Well, Figure 5 breaks down these results by category on the OS World benchmark. This bar chart compares the optimized model, shown in solid blue, against leading baselines like OpenCUA and UI-TARS across specific applications. Across the board, the optimized QN3 model consistently takes the lead. The improvements are especially sharp in complex tools. For example, look at the spikes in accuracy for GIMP, Thunderbird, and versus S-code compared to the striped bars. On the far right, the overall cluster summarizes this success, where the method achieves a final accuracy of 40.2%, setting a new state-of-the-art. Okay, Figure 7 reveals the training dynamics behind these results. The first 3 panels show the environment expansion for the GUI, text, and coding agents. The rising blue lines indicate that new tasks are accepted linearly, providing a steady stream of fresh challenges. Crucially, the flat gray lines show that accuracy on these tasks stabilizes near 50%, meaning the system effectively maintains a moderate difficulty level. On the far right, the response length plot shows a sharp initial rise in token count, suggesting the model learns to reason more thoroughly before acting. Wrapping up, 2 big takeaways stand out. First, jointly optimizing the environment and reward model alongside the policy creates a much stronger feedback loop than training them in isolation. Second, These automated reward signals can actually outperform human supervision, which is a major step towards scalable, self-evolving agents. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.